For this paper, we performed a critical analysis of bias mitigation techniques. First, biases are spurious correlations that the models may find it easy to exploit but otherwise lead to poor generalization. For instance, in the commonly used celeb A dataset where the task is to predict hair color, gender acts as a source of bias, with blonde-haired male celebrities occurring very rarely. So, the methods tend to fail on such a rare group. Multiple bias mitigation techniques have been proposed to address this issue. They can roughly be divided into two categories, the first of which is the explicit methods, which require bias labels during training. For instance, for celeb A, these methods may use gender and hair color labels to create four groups and then balance them out. Implicit methods, on the other hand, do not have such an assumption of requiring bias labels for training and may use some indirect way of detecting and then mitigating biases. All in all, methods from both of these categories tend to show large gains on datasets such as celeb A. But there are multiple critical issues and open questions regarding these methods. The first of which is that most of these methods are only tested on a few bias variables or groups, such as the four groups in celeb A. So our question is whether or not they can scale up to multiple types of biases and a large number of groups. Second issue is that explicit methods assume that all of the bias sources are annotated, but can they function if some of them are hidden? Finally, most of these methods are tuned on test distribution, which is completely unrealistic. So how robust are they to the choice of tuning distribution? We explore all of these questions on multiple state-of-the-art explicit and implicit methods. For this, we built a dataset called BiasedMNIST, where the task is to recognize the digit, just like the original MNIST, but there are multiple bias variables, such as foreground and background colors, like ones are usually green and appear on purple backgrounds, and there are in total 7 of such confounding factors, leading to a large number of possible groups, much more than the celeb A dataset. For the natural dataset, we chose GQA-OOD, which also has a very large number of dataset groups. There is imbalance in terms of group and answer distribution, making it a challenging setting. All in all, we find that the explicit methods are unable to outperform baselines on datasets which have a large number of dataset groups. Implicit methods, on the other hand, show promising results, outperforming both baselines and explicit methods on challenging benchmarks. For our second question, we wanted to see if the explicit methods could function even if some of the bias variables were not provided during training. For this, we used a BiasedMNIST dataset and systematically hid some of the variables. All in all, we find that no matter how many variables are shown or hidden, the explicit methods still remain below the baseline and the implicit methods. Finally, we wanted to test if the methods were robust to the choice of tuning distribution. For this, we varied the tuning distribution from distributions which amplify training biases to distributions which invert the training biases. All in all, in celeb A, we find that the methods are highly sensitive to the choice of tuning distribution, showing very large variance, especially on minority groups such as blonde-haired male celebrities in celeb A. Finally, we recommend that our evaluation protocol be used in future methods as well, and our code is available on GitHub. Thank you.